Sir, if you permit, then we can start the sessions. Sir, is my voice audible?
Yes, I'm sharing my screen. I sent you one message, so please you could also check your message. So, okay, so good afternoon. Let's continue the lecture for today. So today we are going to talk about the continuation of a sliding mode control. But basically, as you remember that yesterday, day before yesterday, so we talked about the introduction to a sliding mode control, and we also looked at some fundamental aspect of this control technology. So today we will continue again. So about the sliding mode control design, and then I will show you some different kind of result has been developed based on this strategy. Of course, a sliding mode control, variable structural system VSS, so it has a long history in control. So therefore, many extension, many development, many application you can expect for this strategy. So based on the two fundamental aspects of the sliding mode control, it become of interest. The first, it was the finite time convergence. It means that the state trajectories can approach to some surface and can be regulated in the finite time. The second property for the sliding mode control is the robustness. And that's it based on these two aspects. So we can continue to look at the more basic features of the sliding mode control in the lecture today. So today I have prepared some lectures based on a schedule. First is a continuation of a sliding mode control. I will talk about the fault, about the tolerant control, fault diagnosis, and also I will also give some lectures about the cybersecurity and particular applications to autonomous cars. So that's it for today. So basically we can cover this important aspect in our lectures. Okay, so let's continue. So about the sliding mode control, as you remember that one of the important things, so you need to basically to to find this sliding manifold, sigma x. Okay, so the sigma x could be the nonlinear function. So you should think about some sort of a linear form. So either you can choose linear or nonlinear shape. But anyway, so this is a sort of a manifold. It means that they can attract so all the trajectories so to one particular surface. So this manifold sigma x, so in the linear form, for instance, you can define it like this, Cx so equals 0. So here you can see that the parametric C, so the metric C is basically your design, so design parameter. So you need to choose the metric C. But of course, it's not limited to this shape. So as I said that the sigma x also could be nonlinear, but depends to your case. So it depends how do you want to look at the control design, and that's it. You can look at the different manifolds, so in your case. So there is one issue we need to clarify. So the issue is that how is the sliding manifold design when one of the previously described canonical form is selected? So if you remember that we talked about the four type of the canonical form in our lecture before. So now the point is that if you have one of these particular canonical form, so how this sliding the manifold can be designed? So this is one question. So basically, and this means that, so this question means that you are talking about some classical control design. So in such a way that you have a canonical form in the system model, in the dynamics, and also you try to design the sliding manifold so that based on this strategy. So in this case, we can see that in the case of the design of the sigma x for the canonical forms, so let's start with the reduced form. So you remember that the first techniques we taught in the canonical form, so in the shape of the reduced form. So we know that if you look at the state vector, so it can be split to x1, x2. So it means that your vector x, so you can represent it like x1, x2, okay? So you can split it into two parts. So when you split it into x1, x2, and then you can design sigma x like this. So sigma x is composed of x1, x2, like this. And then you remember that the sigma x, it should be c multiply x. Okay, this was the linear shape. So now the x is the x1, x2. So now this is the x1, x2. And also the metric c also can be partitioned to c1, c2. And therefore, so this could be the representation. Okay, but if you're doing like this, because you want to reach the reduced form is a function of x1, okay? So you remember that the reduced form should be in the function of x1. And therefore, x2 should be get rid of x2 in your formulation. And that's it. From this mathematics, you can say that the c1 x1, so plus a c2 x2, so this should be equal zeros. And then if you want to get explicitly the reduced form in the shape of x1, so what does it mean? It means that the x2 so should be removed. How to remove x2? So x2 from here should be minus a c2 inverse of the c1 x1, okay? So now from here you can see that if you want to get x2, the x2 should exist, okay? So it means that you should calculate it. And if x2 should exist, it means that the metric c2, so the metric c2 should be basically the full rank, okay? So it means that you should be able to make the inverse. Okay, so now the metric C2 is a non-singular, and that's it. You can calculate X2, and then when you have X2, it means that the X2 becomes this, and then if you put X2 in your mathematical formulation, So then you can see that the x dot 1 is this, and then x is the x1, x2, right? And then instead of x2, you can put this. Okay, so this representation, so in a sliding mode, so the system has such a behavior. There is an algebraic relation. So this formulation, it says that there is some sort of the algebraic relation between the x1, x2, and here you have basically the dynamics. So here you have a dynamics. Okay, so this is the philosophy for a reduced form. And now you see that the task is very simple. Just you need to find C1, C2, and therefore the question is how to find these matrices. So in the reduced form, so if the A1 is linear, so if A1 is linear, so here, so that this is a function of AX and T. So if your function axt is a linear, for instance, like this a11 x1 plus a12 x2. So in the case of the linear, basically the function a, so then the reduced dynamics become this. So now you will get this these dynamics. So for the overall system on the sliding manifold. So the interesting point is that here you have a new matrix. So this matrix, and if or this matrix. So if you choose the matrix F, so basically is equal minus C2 inverse C1. Okay. So based on this selection F, you have this mathematical formulation. So now the whole stability goes to the eigenvalues of this matrix. And therefore you can choose F. You can choose F. So basically, if the A1 and A12 is comparable, okay? So in this case, you are able to choose it. But you know about contrariability. So here it says that A11, A12 is comparable, but the contrariability, so this condition has some sort of some constraint on the selection of A11, A12. But if A11, A12 is not comparable, so I can tell you that the if, so A11, so A12 is not, so it's not fully comparable. It's not fully comparable. So what should we do? So if it's not fully comparable, so you need to check a stabilizability, okay? So you need to check a stabilizability. So in control, we have a two concept. One concept is the contrariability. The second concept is a stabilizability. These are totally different. So these are not equivalent, right? So the contrariability means, so this matrix A11, A12 should follow some rank of some formulation. So you know from the control course. So if there's such a contrariability matrix, the rank is complete. The system is fully contrariable. But in such a way that this is not contrariable, you need to check a stabilizability. So I can give you one example. What does it mean? What does it mean, a stabilizability? So assume that you have a function gs, okay? Let's assume that you have a function gs, okay? So gs is equal 1 over, for example, s plus 1 multiply s plus 2. Okay, so if you have such a transfer function, so this, if you find the matrix A and matrix B, if you find the matrix A and B, so for this matrix, so you can see that this system is a fully comparable. So it means that this system is comparable, okay? So you can find it as a comparable. But if I give you another function, for example, if I give you gs, for example, s plus 1 over the s plus 1 multiply s plus 2, okay? So this transfer function is equal 1 over s plus 2. So what happened here? S plus 1 goes by this, okay? So this system is not controllable. It's not controllable. Why? Because S plus 1, so S plus 1, so it says that S minus 1, so this mode is not controllable. It means that this mode you cannot control. But this system is, but this system is stabilizable. What does it mean? It means that this S minus 1 is stable because S equal minus 1 is stable, okay? So this is very important. In control, there are four concepts. So two concepts for control design is controllability and stabilizability. And another concept is about the observability. So it means that we have the same concept about the observability. And also another topic is the detectability, okay? Detectability. So that's it. Always when I'm teaching the control course, I will tell to students these four concepts. So the first concept is this, controllability. The second concept is stabilizability. The third concept is observability. And the fourth concept is the detectability, okay? So when you study and if you write the article, and if you write here, if A11 is controllable, so your assumption is very conservative. So that's it. You can also change it to a stabilizable, okay? If A11 and A12 is stabilizable, so it means that stabilizability, it has the large area, okay? It means that for both cases, if A11, A12 is stabilizable or is controllable, then it's possible to choose F such that the eigenvalues so can be assigned. So this looks like a pole placement. So for example, in control, so you can use the pole placement, and then you can basically choose the matrix F. So there is a lot of formulation like the Ackermann. So you can use, for example, the Ackermann approach to choose matrix F. Okay, so now when you have the because the F is this, and when you choose F, now you have a two parameters, C1, C2, then it's up to you how to choose C1, C2. So therefore, based on C1, C2, then you will get the Cx. So sigma x is the design. So it means that you finally, so you can design it, you can construct it. Okay, so this is the main idea. So the main philosophy basically for choosing the sigma x for the reduced form in the canonical form. Okay, so another form, it was the controllability. So you remember that the second canonical form is the controllability form. So what does it mean? If you remember that in the controllability form, the system can be split into the m subsystems. It means that you can split the system to the several subsystems, for example, m subsystem, and then the sigma I. So for each subsystem from 1 to n, it can be designed from this formulation, sigma I transpose xi. But you need to remember that here the vector x, so it can be composed to the several x1 up to, for example, xn. So this is a several subsystems. And then each x1, it has a dimension n1, for example, and xn, it has a, for example, dimension, for example, another dimension like nn. So now the whole dimension should be equal to dimension n for the vector x. Okay, so now the point is that the major requirement how to choose CI, because here you need to choose CI for each subsystem. So you need to choose CI such that the overall control system in a sliding with asymptotically stable. So it means that each subsystem should be stabilized and then depend on the choice of CI. So the dynamics of each subsystem in a sliding mode can be assigned by selecting the component of CI. Okay, so the question is, how to choose the parameter of CI. So now each equivalence subsystem has the order ni minus 1. It means that this is the order for each subsystem. So it has such an order, and it has a canonical contributive form. And then you can find the corresponding characteristic polynomial has the component of CI as the coefficient. Okay, so this is just the partitioning. So you need to partition X to the several subsystems, like the M subsystem. And then you need to choose for each subsystem sigma I, you need to find CI. So not the questions that how to find CI, but you need to choose CI in such a way that each subsystem should be asymptotically stable. Okay, so another form we discussed also in our previous lecture, it was about the decoupled input-output form. So you remember that when we talked about the decoupling input-output form, so you need to look at the degree of the system, and therefore, so it's very similar to the case of the contributive form. So that's it. The approach for this case is also very similar to the contributive form. So because if you remember that if you back to our decomposition, because we talked about the contributive form here. So this was about the decoupled input-output form. You remember that we discussed about it in the last lecture. So you need to look at the relatively degree R, and it means that for each subsystem, you have a different relative degree R1 to Rn. And then if the R is equal n as the order of the system, then you can find this shape. And for this system, you need to find the decoupled input-output form. So in this shape, you need to take a Ri derivative from the Yi such that the Ui can be appeared. So in this case, this is your decoupled form, and this decoupled form. So if you find it, is very similar to the contributive form, and then you can basically to apply the same idea for this case. Okay, so then now you can see that the decoupled input-output form is also very similar to the contributive form. So another shape, it was about for the canonical form, it was a normal form. Okay, so the normal form, so basically, this also can be called as a zero dynamics. So what does it mean, the zero dynamic? The zero dynamic, it says that there is some internal dynamics, so they can bring the zero to the output. It means that it can be obtained by posing equal to zero the output. So how to bring the output, for example, equal zeros? So in this case, and also, of course, then also the derivatives. So in this case, you can see that the output is zeros. And in this case, you need to find some zero dynamics like the eta. So the eta here is the zero dynamics. So in this case, if you want to design the sigma x for the canonical form in the shape of the normal form, so you need to choose the basic the zero dynamics should be asymptotically stable. So how to make it a typical choice for a sliding variable component for the sigma x. So you can choose a sigma x, for example, equals zeros. You can choose sigma I like this. Sigma I is a CI transpose ZI, but you need to remember that for this case, sigma I, so sigma I is chosen as in the contributive form. So the basic is that if you understand the contributive form, so easily you can handle a decoupled form, you can handle normal form, because the selection of the CI is very similar to the contributive form. So to assign the dynamic to for the reduced order form. Okay, so now you can see that this is another basic the canonical form, and it's very important because you remember, you know that zero dynamic is very important in control. Why? Because the zero dynamic is an internal dynamics, and it brings the output to zeros. And if you don't control it, then the system becomes in a very critical situation. Therefore, stabilization of the zero dynamics is the first thing we should do. And therefore, how to stabilize, how to asymptotically stabilize the zero dynamics, you can do it by choosing the sigma I in such a way. Okay, so now the existence of the sliding mode. After the design of the sliding manifold is necessary basically to guarantee the existence. So the existence of the sliding mode, so we need to look at it, how to guarantee that the sliding mode exists. So a sliding mode exists if in a vicinity of the sliding manifold sigma x zeros, the vector tangent to the state trajectory of the control system is always directed toward a sliding manifold. So it means that if the state are hitting the manifold, so the tangent is always should be in the direction to the sliding manifold, and this means that the sliding mode exists. Okay, so in this case, around of the sliding manifold sigma x, so the vector tangent to the state trajectories, so always directed towards the sliding manifold. It means that the state should remains more or less after the some time, or the remains or stabilize on the manifold. So if this condition is satisfied, then we can guarantee that a state can be stabilized, can be basically remain on basically on this case. Okay, so now the existence of the sliding basically the mode. So the ideal and practical sliding mode. So what are the ideal and the practical sliding mode? So the ideal sliding mode is enforced if the state trajectory of the control system is such that the sigma x zero. It means that if the reaching time, because we talked about this before. For example, if this is your sigma x, so if from the initial condition x zeros, if the state it arrives to this at the time tr, this is the time tr, okay, x at the time tr. Okay, so after the TR, for each T bigger than TR, so a state should basically remains on the sigma x. So basically this part is the reaching time. Reaching time is this, and this time is the motion time, or we call it the sliding motion. So a sliding motion. Okay, so this sliding motion or the chattering, so this should be controlled. Okay, so this is basically the ideal. Of course, we would like to keep it as far as possible equal zeros. But to have an ideal sliding mode, the control variable has to switch at the infinite frequency. So this is not possible, okay? So basically the ideal case, so maybe not possible, and therefore we should say that if not possible, so we should say that the sigma x, so this should be approximately zeros. So this approximation means, so this motion, right? This kind of the motion, and in a sliding mode we call it as a chattering. Okay, so now the topic of the chattering so it becomes on the table. So now in this slide there are two information. One information is the reaching time, is a TR. Another is about the chattering. The chattering is for the each time, so there is a bigger than basically TR. Okay. So now what is the task? The task is that first you need to bring a state to the surface. This is a phase one. Okay. The first step is this. So, and then you need to design the control. You need to design the control in such a way that it remains arrive to the surface in a short time. And then the chattering also should be controlled. So a state evolution in the vicinity of the sliding manifold is called the practical sliding mode. So then now you can see that the PSM, so the practical sliding mode, so it also represented the chattering. So you need to remember that how you can how you are able to reduce this oscillation, how to reduce this oscillation. So I can tell you that usually when you design the control signal in a sliding mode, so for example, you have some coefficient, for example, some coefficient, to multiply the sign, okay? For example, sign of x. So this sign of x is gives some switching, and therefore this is switching. So we talk about this switch. So this switch, it means that you have some sort of a sign function, okay? So therefore, if you want to make it a PSM as a practical sliding mode, so the sign function, so this can be approximated. So this can be approximated, for example, with another function, for example, x over the for example norm of x plus epsilon. Okay. So this is a very interesting trick. So this we call it a trick. Okay. So the trick is like this. So when you design the sliding mode control, so I told you that the system should have some switching in the control signal. But this switching, it needs a lot of energy because you cannot do the infinite frequency. So therefore, usually in a sliding mode control, if you want to get more smooth and if you want to control the chattering, or if you want to come to PSM, to practical sliding mode, so the sine x, because you know that the sine x is the x over the norm of x, right? Because we know that the x over norm of x is a sine. But you need to add something here, and therefore you can change it like this. So this epsilon is too small, okay? So by adding very small values of epsilon, so you can avoid so this kind of this infinite switching, and you can also get a quicker or a smooth response. And this is basically we need to do it in our sliding mode control design. So sometimes when you get a control signal like this, so the first question you will get from the reviewers ask you that how is possible to apply this control, because you should have some sort of the switching in your control. So and the answer is that you can modify the control signal like this, and then you can basically get a much smooth response. Okay, so this is basically what I'm talking about, the ideal and practical. So this is basically the ideal case. Ideal, it means that we are reaching time at the time TR, okay? And then for each time bigger than TR, so you should have exactly zeros, okay? But this is not possible, because this is not possible to make it. And therefore, you need to accept some oscillation like this, okay? So this is a chattering, and therefore, if we want to reduce the chattering, so you can modify, here you can modify control. So you can modify control signal, for example, the sine function. So sine of x, you can change it to x over x plus epsilon. Okay. So now you can see that you can control, because this chattering, so this chattering also should be controlled in such a way that so the range should not be too high, and that's it. This is the art of the control signal. It means that your control signal UT, so is a big challenge for the PSM, for the practical sliding mode. Okay, so the existence problem. So the existence problem is a stability problem. So the first thing that you need to satisfy is a stability. So stability should be guaranteed. So a existence of a sliding mode requires that state trajectories at least from the neighborhood of the Sx equals zeros, it means the attraction region tend toward a sliding manifold. So it means that the system should attract. So the attraction region around of this neighborhood of this sliding surface. So basically, the all should basically should attract, should be pushed toward the sliding surface. So the existence of this sliding mode has such a requirement. So the attraction domain, because attraction domain, it depends which initial condition, where your state at this moment exists. Because maybe you cannot do it for any initial conditions. For some initial conditions such that a state is around of this or the neighborhood of Sx equals zeros, so this attraction domain can coincide with the whole state space, and then you can basically predict it global. So this is very important. If you want to have a globally reachable sliding mode, it means that for any initial time, because this initial condition at the time zeros, for any state at the time zeros, so you want to do such a the basic stabilization. And that's it. If you want to satisfy the reachability for all the global state, so it means that if your attraction domain can coincide with the whole state, then you have a global reachability. So existence of a sliding mode can be proved by using the Lyapunov function. So that's it. For stability, we always use the Lyapunov base, and therefore you need to choose what is your Vx. So the Lyapunov function Vx, so this should be designed, and how to design it. So this is the task. Okay, so the first step is existence for a stability problem. It means that you need to choose the function Vx. Okay, so now there is a lot of research. So many researchers, they develop many Lyapunov functions. And if you choose the new Lyapunov function, then you can design the new control. And therefore, the main task for the researcher in this area is to pay attention how to develop a less conservative Lyapunov function. So it means that if you choose the less conservative design, so it means that you can reach to more global, so for example, the reachability. So basically, this means that we need to pay attention to Vx, and this is a very important task. So the one simple Vx. So one of the simple Vx, why not choose against sigma x? Because you remember that the sigma x is a one variable, right? As a sliding manifold. So why not choose Vx based on sigma x in the quadratic form? Okay, the half of the sigma x two. So this function, so basically is a positive. And also you can also check it out with, and then you can check out what is the v dot x, okay? So this should be calculated. So you need to remember that the sigma dot depends on the control variables. Then it's a discontinuous on the sigma zeros. So you remember that the sigma x, it depends on the control variable, and control variable u, so it has some switching. This has some switching, and therefore at the sigma zeros at the sigma zeros there is some discontinuity. Okay, we need to remember in mind. So you need to remember that this point. But if you want to take a derivative, the control variable has to be chosen and such that the attraction region, the v dot x, so this relation should be satisfied. So okay, so one question for you, how to calculate it, how to calculate v dot x, okay? But the question is how to calculate v dot x. So v dot x is a dv over dx, right? You know from for example, dv over dt, okay? It's a dv over dt is a v dot x. But the dv over dt, because your function dx depends to sigma x. And then you can say that the dv over dt is equal to dv respect to the d sigma and multiply, so d sigma over dt. So this is a basically you have a chain rule that you can use the chain rule in mathematics. So by using the chain rule, so you can write dv over dt is equal to dv respect to d sigma multiplied d sigma over dt. Okay, so dv respect to d sigma, so vx is a this, and then you can see that the dv or the round of v, for example, round of v respect to the sigma, so it's equal half multiplied 2 multiply sigma x, okay? And therefore, this becomes sigma x. So here, then you can write here that the round of v respect to round of sigma, this becomes sigma x, multiply round of sigma over dt or d sigma over dt, this becomes sigma dot, okay? So that's it. When you have this formulation, so we need to remember that how to calculate, because this derivative, you need to know that how to make it. Okay, so v dot x becomes sigma sigma dot, and then the vx is positive, so v dot x should be negative, okay? And then this relation should be satisfied. Okay, so for by choosing the control signal, so this condition should be satisfied. So for the reachability condition, so v dot x basically should be the negative. And what does it mean? It means that your state trajectories, it means that your state trajectories for this sigma x, so this state from the x at the time zeros, they can reach to this at this time. So this was basically the reachability condition. Okay. So if you want to keep it to satisfy this condition of the time tr, so you can satisfy this condition. So if you satisfy this condition, it means that your state trajectories can move basically to the surface. Okay. But of course, after this, there could be some sort of a chatter. So now we come to prove the finite time. So if you want to look at the FT, because FT is one of the important aspects of the SMC for a sliding mode control. So we need to look at the finite time convergence is very important. Okay, so one alternative way to express the reachability condition is the following. So for the sake of simplicity, the single input case is considered. Now we have only the single input for the single input. So sigma dot, so it should be negative, right? So then we can change it to this. So we can say that the sigma dot should be less than minus the gamma, the norm of sigma. And this is and also for the reachability conditions. So the gamma should be positive. If we choose the gamma positive, and if this condition is satisfied, of course, this means that this is also negative, and this is also true. So if you want to satisfy this condition, so it means that the v dot x, because this is a v dot x, okay, this is a v dot. So the v dot x should be less than minus gamma prime of the norm root square of the vx. So because you know that the vx it was like this. It was the half of the sigma x, okay, a square. And from here, you know that the sigma x, it becomes a I hope everything is, you can hear me. So sorry, I don't know why my mic, it was unmuted. It was muted. Okay, so now we know again, I can repeat it again. So the finite time convergence, so basically is a property for the SMC. So for the reachability condition for the single input, so basically we can do like this. Instead of saying that the v dot x, so it should be the sigma that should be negative. You could substitute by this term minus a gamma norm of the sigma because this is also negative. So from here you can see that the v dot x is less than this term because the vx, so the sigma x, the norm of sigma, you can substitute it from this formulation. So here, and then you have this mathematical formulation. So this mathematical formulation, so if you look at the differential equation and the solution for this, so it's possible to find so the upper bound for the reaching time, TR, by integrating the gamma reachability conditions, so between the time zeros to the TR. So now if you look at the solution, because here usually there is some lemma, so there is some lemma, but it can be proved. So there is some lemma says that if this condition satisfied, then you can reach to this condition. The sigma at the TR minus the sigma at the time zeros. So it also the less than these conditions. And it means that from here, so you are able to find the TR, the reaching time less than this. So reaching time less than the norm of sigma zeros less than the gamma, this is FT. It means that you can guarantee the convergence in a finite time, and the TR is a bounded. You see, it's less than infinity, and that's it. Is a finite time convergence. So this property is very important. And of course, if you play with the gamma, because it depends to your gamma. If you change the gamma, you can also change the TR. So if you want to, for example, if you want to decrease the TR, then the gamma should increase, okay? The gamma should increase. But you need to pay attention that if the gamma increase, then you need to see what is the control, because the control signal should be not saturated, because another problem is about the saturation. So now you see that this trade-off. So this trade-off between the fast response and also the saturation, because you need to pay attention. So how to find how to choose this gamma, because by changing the gamma, basically you can change the speed of the convergence. Okay, so here there are some interesting textbooks for you. So if you are interested, you can also look at some fundamental aspect of the sliding mode control. So there is a lot of interesting works. So from the Professor Etkin, so from Professor Ferrara. So there is a lot of interesting textbooks, so you can find it for your interest. Okay, any question up to now? Or? Okay, so if there is no question, so then I can also show you some other results about the slide remote control. Okay, so I want to show you some new results. So basically, okay, so now I want to show you a little bit how this kind of basically a sliding mode control. So can be added to the network control and also with some complexity from CPS. So the topic I want to, yes, do you have any question? Yes. Okay, please. I think you have a question. You can ask me the question. Okay, Desi, do you have any question or you raise your hand? Okay.
Sir, what is, excuse me?
Yes, yes, please. Okay.
Hello?
Okay, what's your question is?
Sir, finite time, fixed time, stability.
Okay, so about the final time. Okay, we noticed that okay, so I can explain you here that for SMC, so a sliding mode control, so it says that I have a property of the FT, the final time. The final time convergence, so we notice that it depends basically to the reaching time. It means that the TR is less than, for example, sigma zeros over for example, the gamma. So it means that this is a less than infinity, and therefore this is a basic, we call it the final time. So the final time means that it reach in a short time, but this is a finite time, not in the infinite time. But of course, we notice that if you want to get the fast the response, if the TR decrease, so now you can see that the gamma should increase. But if you increase the gamma, then you can decrease the TR. And if you decrease TR, it means that the final time convergence, it becomes faster. But of course, there is some problem. The problem is that there is a trade-off between this case. You need to look at the control signal, okay? Because the control signal, so it should not saturate, because if you increase the gamma, so maybe the control signal will be saturated, and therefore you need to pay attention. You cannot increase it too much. There is a gamma max, okay? For example, for the gamma max, in order the system not saturated, and for the gamma max, and then you can find the TR as a basic the TR mean. It means that how much you can make it the system fast. So this concept is a finite time, but in control, we have another concept about the fixed time, okay? So the fixed time, so fixed time is also very important topic. So the fixed time, it means that so your TR should be exactly at the given time, for example, the T as a T given, okay? So it means that based on what the parameter T, so you like it, you have it, then you can design the control. Okay, so if your TR in the fixed time, if your parameter T for the reaching time. Based on this formulation, so you can you see that the fixed time is more difficult than the finite time, because the finite time you can be between the one up to the TR mean, but here the T is given. But of course, you can follow some extension, some modification of a sliding mode, so such that you could be also able so to satisfy the fixed time. So, but in fact, I told you also in the last lecture. So these two topics are different. So, but the difference is that you need to pay attention that if the fixed time is doable or not, because sometimes you cannot make it by the regular sliding mode, because a sliding mode, you have some constraint in terms of the selection of the fit final time based on the gamma and based on saturation. So now usually if we look at the research, so there's some research is also looking at the fixed time and also finite time. So that's it, you need to distinguish. You need to distinguish between these two parts. But today I just talked about the finite time, but the fixed time is also should be the modification. You can modify your sliding mode control also to be able to satisfy the fixed time. So, but I didn't discuss it today, but if you are interested, I can send you a few of our publications. So we have done some work in this area. I can send it to you. Okay, any questions?
Sir, can you hear me?
Yes, yes.
Sir, one more keyword is there in the literature, what is predefined time stability, which is also tightly associated with the sliding mode control and its variants. So, if
Okay.
time permits and if it is convenient to you, sir, then please also give some lights on this predefined time control stability.
Okay, thank you. Yes, predefined,
Yeah.
predefined time stability. So it means that so you are sometime as I told you that the predefined. So the main concern is about the final time. It means that you try to define it. But this definition is different from the fixed time. The fixed time, the time should be exactly the objective. But in the defined time, so it means that you are gradually reaching to the final time. That is exactly what I presented here. So for the predefined stability, so it means that you need to satisfy some bounded for the reaching time, and therefore you can basically you can do the exactly using the sliding mode control. So this is predefined. So basically, these are the some keyword basically for the addressing these two topics, the finite time or the fixed time. So the point is that in the predefined, if your objective is a fixed time, so the traditional sliding mode control only can guarantee the finite time, and then you need to see how to satisfy the exact time. So, but exact time. So, if you look at again the same formulation I showed you before, because we have this formulation v dot x, so it was less than the minus the gamma root of Vx. So all the discussion comes from here. Okay, so this formulation is for stability. And therefore, so this stability is for the given time. If the time belongs to, for example, the one the zeros are up to the t mean. So it means that if your object, if your target is the final time, so then you can do the SMC. Okay, then this is okay. But if your target is a fixed time for the given time or the predefined, so a stability time, a stabilization time, then you need to see how to make it, because this condition, you need to reach to the equality, because you need to satisfy it for exactly the same function. But I can tell you that predefined or the fixed time, so it can be also possible by doing some modification of the Lyapunov function, because this Lyapunov function dx, because this Lyapunov function dx is only can give you basically the finite time. But if you want to reach to the fixed time or the predefined, so we need to modify the Lyapunov function such a way that we can reach to the exact time. So what is the problem? The problem is that if your fixed time is become less than TR mean, for example, if your fixed time So if the fixed time, so if the fixed time is less than the TR mean, so this is a problem. So this is a problem because you cannot go below of this value. Because if you go below of this value, then you have a saturation problem. So basically, for the control signal UT. And therefore, if you want to avoid this condition, if you want to avoid this problem, so you need to come back to your Vx. So you need to come back to your Vx and try to modify it. So now there are some publication, I remember that one of my PhD students, so she also published a few papers about this predefined and the fixed time. So I can send you this publication. But in fact, the main task is to do some modification the Lyapunov function in order that we could satisfy to solve this problem. So as I told you, this is a very good formulation. So this formulation is very interesting, you see. So you cannot increase gamma too much, because if you increase gamma too much, then you can get the problem from the basically the control effort or the saturation. I think if you are interested, maybe I can share with you some publication, but we can discuss it because there are some issues maybe to be discussed individually because these are more or less the topic is the same, but in fact there are some difference in the selection of the Lyapunov function. Okay, so let's to show you some result about a sliding mode control and for some complexity. So I told you about NCS. I think you know about NCS. We discussed it before about the network control advantage, and we discussed about the CPS, and we also look at this challenge about state awareness, data circulation, real-time analysis, and also the scientific decision and also precise execution. So we discuss also about the computation control. But when it comes to the basic data to the CPS and also network control, so we know that there are three parts. One is the plant, network, and also control. But also I'll show you, we discussed about these three problems in the last lecture. But what I want to tell you today, so I want to tell you some complexity in the plant, because the first thing in the CPS or the NCS, so the first part is the plant. You see, the plant is the number one. The plant, it means that how to model it. So sometimes the dynamics are a bit complex. And that's it in my research, because I did a lot of research on this kind of the system as a Markov jump system or the NJS or the semi-Markov jump system SNJS. So usually there are many CPS systems, so many CPS, so that they can basically can be modeled as a Markov jump or the Markov chain. The status of the system is changing. So the physical system may suffer from the abrupt structural change, okay? So for instance, in the sudden environment disturbance or unexpected change of the operating point or the parameter shifting. So for example, in the circuit, if there is such a switching, you see, between 1 and 2. So this switching, it means that you are jumping. So there is a jump, okay? So there is a jump from one to 2, or the vice versa. So this kind of the jumping from 1 to 2, and also from 2 to 1, or maybe the system remains at the same status. But this is a probability, you see, this is a probability. So now there is the topic we have in control. So we have a topic of a Markovian jump system. So the Markovian jump system is a stochastic process, but we are dealing with some probability. So the transition from 1 to 2 with the probability of the 0.7, we call it is a transition. We call it as a transition probability. Okay, the transition probability. Okay, so we call it the TP. Okay, so for the TP 0.7, the system goes from 1 to 2, or with the probability 0.3, it remains at 1. So now you can see that 0.3 plus 0.7, so it's equal 1. And this is also the okay from mathematics. So for the system number 2, it goes with the TP. Is a TP the 0.6 remains at the same system, but with the 0.4 goes to here, again the summation becomes 1. But I can tell you something about Markov jump. Markov jump has been developed a lot in the past. So I did a lot of research maybe 10 years ago or even more. 15 years ago, I did a lot of research on Markov jump. And currently, my students are doing also a lot of research on the Markov jump. But I can tell you that the Markov jump has developed a lot. But one problem, the problem is this. So these are the some problem because these are the information, right? The 0.3, 0.7, 0.4, 0.6, these are the information. But in total information, it doesn't exist. We don't have. So if we don't have this kind of information, if we don't have this information, so what should we do? And that's it. So there is a lot of research on the uncertain TP or the unknown TP. So I want to tell you that the context of the Markov jump, the Markov jump system has been developed a lot. For the full given information, it means that if your information for TP is given, or is the partly uncertain, or the partly unknown, or even the full unknown. So I want to tell you that for all of these cases, so you are able to do some research and try to basically model your CPS, and then try to basically apply different control strategy. So if you are interested about this, so you can contact me because this, as I told you, that this is one of our research areas. So let's back to the problem. The problem is that for the system description, so x dot is ax plus bu, and this is your initial conditions. But you can see that the matrix A depends to RT, okay? The matrix B depends to RT. So it means that this system is a Markov jump system, and X is a state vector, A and B are the system S metrics, and the UT is a control signal. Okay, so this is the important part. So the RT for the T positive is a continuous time and discrete time Markov process. So now you see a stochastic process. It means that the RT gives you some stochastic process, a Markov process. So what does it mean? It means that this RT, this set, it gives you some fixed value. It is so it takes the RT, it takes the values from the fixed set S, this set from S is equal 1, 2 up to S. So what does it mean here? You have a S jump, okay? So the number of jump, or you have the SS system. So because of the S, it means that you have this number of the system. The system is switching between the S systems, and then your RT, it takes one parameter from here. So now the RT, so this set basically belongs basically to the S, okay? So in this case, so as I told you that the meaning of the RT is a transition from the current state, this state I, to a state J. So the probability or transition to the at the after the time h, the transition to RT plus H equal J for the given RT equal R. It means that what is the probability goes from a state I to a state J, okay? So this probability is represented by this formulation. So this is equal pi ij. It means that this probability is a pi ij, and this is the definition in the Markov chain. So that if the I is not equal J, so the pi ijh is a transition probability. And if it remains at I equal J, is a pi ii. So, and what is the H? So the parameter H is also one offset we have for the basic, we call it as like a sampling time. So it means that this parameter H, you can control the timing between the switching from one state to another state. So, but this parameter H also could represent also the topic of the semi-Markov chain. So that's it. So this is also very interesting. So the parameter H is become more important in the SMJS, in the semi-Markov process. Okay, so the pi ijh is the transition rate. So at the from I to T, time T to the mode J. Okay, so now if you want to make it the H is too small because H is the time, right? So it's like a sampling time. And it's become more important in the context of the semi-Markov jump because in the semi-Markov jump, your transition are the function of H. So if the pi ij depends on the H, you have a semi-Markov process. But if it only Pij, it becomes, for example, Pij, so independent of H, then you have the topic of the Markov process. So now there is also one condition that, as I told you, that this condition for the probability, so should be satisfied, and this is basically some condition we have on the transition rate or transition probability. Okay, so we have proved some theorems for stability. So for this system number one, so the system is statistical stable if there exists some matrices like Pi, so such that this condition can be satisfied. So this condition is the stability condition. So I translates Pi plus summation of the J1 to S, Pijs. So what is the problem here? The problem is H. Because the H is the one parameter for the Markov process, but how to satisfy this condition is a one challenge. So stability of the subsystem, for example, the subsystem from I from 1 to S, because I is from 1 to up to the S, so has no relationship with the stability of the whole systems. So now you see that the Pijh plays a key role in the performance. Okay, so the Pijh is very important. So basically for the stability and also the performance of the whole system. So just for your information that I told you before that this matrix pi, so this metric is a metric for the Markov jump process. These are the information. So I told you before that these are your information. If all is given, is a full information. Maybe some parameters are unknown, you see? So this means that you have some unknown terms. So now you can see that one challenge is propose a feasible stability condition when the transition rate are uncertain or unknown. Okay, so that's it. So we can say that one set could be all the transition, so should be given, should be known, or maybe some parameters for some index. So Pij is unknown. So that's it for the matrix transition rate. So full information, some unknown terms, So that's it, or even some uncertain terms. In total, there are some classification. Some classification for these subsystems. It says that maybe some sets basically are is empty or not empty. So, but we have such a classification for the noun and for the unknown, and therefore we can make it such a representation. Okay, but I'm not going to detail of Markov jump, but this is just for your information that in the cyber physical system, so if you want to make it a more accurate or more advanced modeling, so sometimes you need to add some probability-based modeling. So then you can come to the Markov jump. So when you come to the Markov jump, the first thing is this matrix. So you need to look at what information you have. If you have all information, it's easy. But if you have something like this or some uncertain term, the task is difficult because you need to pay attention how to make it such a representation. Okay, but I want to tell you something about a sliding mode SMC for this, and that's it. I'm going a bit faster. But if you're interested, so if you are interested to this particular case, so you can basically look at these publications. So because we have done some research about stability. So for these different cases of the Markov jump, but this is just for your information. You see that for different case, so you can also develop some condition for stability. These are some condition for stability. Of course, you can find from these references. Okay, so the one thing I want to also tell you about the network control for the context of CPS. So we talk about the time delay as a network constraint. We talk about the packet loss, packet disorder. So it means that if there is some network traffic congestion or there we have a packet transmission failures, network delay. So there we need to see that the delay, it can give some disadvantage for the poor performance or even instability. And the packet loss also can give you some consecutive packet loss. So there could be some disconnection of the networks. So in this case, this is about the problem we have. So in the context of the NCS. So the problem we want to solve it, we want to add consider the delay compensation. So if you look at this publication, so we have said that we can represent the lower bound, upper bound, basically for the transmission of the delay in the networks. Okay, so the delay, so the parameter of the delay, like the tau t, so it's a between the tau t is between the dm and also the dm, the capital dm. And also we add also one parameter t. So the parameter t is a partitioning time. So what does it mean? It means that for the time interval from tk to another sampling time, tk plus 1, so we try to divide it to the some sub-interval, so based on the parameter t. So now you can see that for this interval I1 is the tk to tk plus t. The I2 is from this sampling time to this time. So in this case, so you can divide it to the several subsystems. And then this is a very interesting part as a the time delay modeling for each subsystem. For this interval, the time delay can be defined like this: is a t minus IKT. For this part, the delay can be defined like this, and for this part, the delay can be like this. So this is basically we have it the modeling. So how to obtain the model of the time delay for the network system. And that's it. For all of these delays, so they can satisfy this condition is always bounded, and also the derivative is 1. Okay, so if you need, you can find more details so basic in this publication. So now we come back to the network improve efficiency. So the first thing is that we need to look at the time triggering control. So because you remember that if you look at this kind of the TT, because this TT strategy as a time triggering strategy, is a very simple case to send the data over the networks. So, but in the time triggering control, the control task they can be executed in the periodic way. So now you have some periodical sending the data over the networks. But the TT has a problem. The problem for TT control is the wasting the computation and also energy resource of the battery. So the time triggering control is not a very popular approach because it has a higher computation time and also about the energy because the system should be executed in the periodical form. And that's it. You can, of course, you can occupy the bandwidth, and that's it. You cannot reach to the optimal usage of the bandwidth, and that's it. You could expect some congestion in the network traffic. So therefore, in the context of the network control, for example, here and also here, so you need to decide because if you have the data XT and here you have a sampling time XKH. So how to send the data over the network? Of course, the one issue is a delay, okay? So one issue is a delay, but there are many protocols to send the data. One is a TT, but we have also some other approach we can discuss. So another approach is the event triggering control. For example, we can send the data over the networks. So if you want to use the event triggering control, of course, we have also some other lecture to discuss about the event triggering control, but for your information, so event triggering control is one approach you can execute control depending on the predefined event triggering conditions. So in the event triggering control, you have some conditions where these conditions basically should be satisfied. So here you have a parameter, the omega, the parameter rho, and it means that for different sampling time, so these conditions should be satisfied. Okay, so here you can see the error signal. Error signal is the difference between the state at this sampling time, so minus the previous sampling time, xtkh. Okay, I will discuss about the event-based control also in the future presentation, but for your information that in the event triggering control or in the ET, so in the ET control, you should know one thing, the next releasing time. So this is very important, how to obtain the TK plus H. So because if you could obtain the next sampling time, then you can say that you know when the next data should be sent to the networks. So usually there are some mathematical issues to calculate the TK plus 1H. So based on the current time instant, and based on some function, and this function basically so is depends on your predefined ET condition. So if this event triggering condition is satisfied for this minimum value of this time index, so basically if this condition satisfied, so this would be your next sampling time. Okay, so I will also tell you more about this case because usually you need to remember that we have three topics. One is a TT, is a time triggering interval. We have a ET, is the event triggering interval, and also we have also the ST. The ST is a self triggering control. Self triggering control. So also I will discuss it in the next lecture. So about the self triggering control. So it's very important. So now you should know that why this when you need to choose TT and why you choose ET or why you choose ST. So these are the three different strategies. So you can send the data over the networks. So for the event triggering control strategies, this you need to first to obtain one conditions, and then you should obtain what is the next sampling time, the next time instant that you send the data. Okay, so now for your information, so in my group, we have done a lot of research on the ET. So you should know that the simple way is to use a static event triggering mechanism, or even you can move to the dynamic event triggering mechanism. So what is the difference? So the difference here is that in here I told you that there are two parameters as a design parameter. One is the omega, the second is the rho. But if the rho is constant, the rho is a constant, so then you have a static. But if the rho depends to the time, is a rho t, then you can think about some adaptation. And even basically, you can come to the use some intelligent approach. So you can combine it with the neural networks. But anyway, so you can contain basically this kind of the treatment condition. But you need to remember very important things. Important thing is the avoidance of the zeno phenomena. It means that this phenomena so should be avoided because at the zeno phenomena, so there is no data to be sent, and therefore, or even you should not send the two data to should have it the overlap in such a way that the system cannot react to the how the system the control signal can react to the each sampling time. So the zero behavior, so basically should be avoided. And in this state, there are some basically the research, but I can explain you in another presentation about the triggering mechanism, Zeno behavior, how to avoid, how to. These are something we can discuss it later. Okay, so when it comes to the distributed system, so okay, I think we can have a break now. I think it might time. So if you agree, we can have a 10 minutes break. Is it okay? Okay, so we can start after 10 minutes, okay?
ओके सर 10 मिनट का ब्रेक हो गया
Okay, so let's have a 10 minutes break and please come back in 10 minutes. Then we can come.
ओके सर
Hello again. So welcome back to the session. So if there is no question, so I can start continuing with the lecture today. So in this part, I try to bring your attention to one complexity in the modeling from the market charm. And then the second challenge was about the network side and then how to mitigate the complexity of the network in order to enhance the network performance. So we can also look at some new technology based on the triggering strategy, either the time trigger or event trigger or even the self trigger strategy. Of course, we will come back again to this topic in another lecture, but this was just the introduction to the triggering mechanism. But the important thing for us is to look at basically this mechanism of the sending and receiving data over the networks. So if you look at this part from the plants, so if you send the data over the network, so then you can see that basically, so there is some mechanism for the sending the data. So this is sort of a distributed event-driven scheme. It means that for the different data you have, basically from the sensor 1 to the sensor N, for this kind of data, for instance, sensor I, so you need to see that after the sampling, so you have this sort of this sample data. These are the some sample data you can obtain it for after each sampling of your data from each sensor. So now you need to apply the distributed mechanism. So there is a ETC1, ETCI up to the ETCN. So what does it mean? It means that we need to look at the same mechanism for the parameter rho t and also the omega as we discussed before. So it means that maybe you have the rho I. For each event trigger mechanism, you have a different parameter rho I. Okay, so now you have this data. So this data basically, so there has been sent over the networks, and this data can be received basically after the networks. So this data should be stored and then basically go to the network side. So and then we have this zero order hole, and then we have this sort of after the networks. So then you can also design the control. Okay, so this mechanism, so for this ET mechanism, so this is an event triggering mechanism. So sorry, but this event triggering mechanism. So here we propose. So this could also follow this kind of the sending receiving the data. So as I told you before, so there are some conditions should be satisfied, and then this is also the time instant has been released. Basically, the data that has been sent out. So but if you need also more information, so you can look at this publication. So about the distributed dynamic event triggering basically for this kind of a system. So these are the different time interval. So for sending also the data and based on this mechanism. But we will discuss it again in the future. But what I want to show you now about the control design. So the control design is a sliding mode control we are talking about. So as we noticed that the control signal has a sort of a switching between the switching and manifold switching surface. There is a two levels control, for example, U plus, U minus. So we noticed that the first step is to look at the sliding surface. So a sliding surface means that this should be designed and how to choose this CSX or sigma X. We discussed it in our basic lectures. So that you can satisfy the finite time convergence, stability, and also the overall performance. Okay, so a state trajectory at the time TR, it reached to, for example, to the surface is a reaching time. and then you have some sort of a motion or the origin. So we discussed about the reaching time, we discussed about the chattering, but in total, the control signal has a two parts. SMC has a two parts. One is the equivalent part, and also the second part is for the sliding motion. Okay, so in this case, so if you want to bring it in a finite time, so a state trajectory to the predefined sliding surface, so you can design the control signal based on these two formula. But what does it mean, the equivalent control, and what is the US? So we can also look at it in the next slide. So I can tell you that about this Markov jump, we discussed about the transition rate. So usually there is one question. So how will the transition rate affect the arrival time of the sliding surface? Okay, so the arrival time, it means the reaching time. It means we are talking about the TR, okay? What is the relation between TR for the transition rate and also the TR as a reaching time or the arrival time? So you can also call it as a reaching time, okay? The reaching time. So in this case, if you design the sliding surface, a ST as a GX, so GX, it was the linear part, okay? So you can add additional term, and this additional term is an integral. It followed this mathematical formulation. So this is another design of ST. Okay, so here you have some parameter A, B. So you need to know what is the K, the control gain, and so on. But if you choose a ST like this, so you can also obtain the control signal UT from this mathematical form. So, but this control signal, you can find it the reference in this application, because here we use the fuzzy, this fuzzy integral, and that's it. This parameter HI, so this is a parameter from the TS model in the fuzzy, the top of the solenoid. This is for the fuzzy representation. Okay, so in the case of the fuzzy modeling, so by using the different function H, so then you can come to the control signal like this, but the more details you can find in this publication. But you can see that if we change the signal, what parameter in this design, so these are the different transition rate. You see, these are the different TR. For different TR, basically you can find this sliding surface ST with the different parameter signal. So these are the different, basically the function S. It depends on the basically depends on the transition rate, so you can see in this picture. So these are the typical sliding surface. So now the question is that for this typical ST, because we said these are the ST, okay? So for different ST, so you can find a different control signal like this. And then this control signal basically, so can guarantee the stability and also the performance. Okay, so another question is about how to design the TR transition rate dependent SMC. This is a very important topic, TR dependent SMC, when the more information is unavailable. Okay, so we discussed about this TR information like this, okay? So this information is available, but this information is not available, you see? So for this particular thing, because this is your TR, okay? This is your TR. So now the question is that how to design a sliding mode control if the part of your TR is not available. Okay, so now there we can see that in this publication, so if we look at this publication or this publication, so you can see that basically we have proposed control signal like this. This is the TR based SMC. And here we have a several parameter rho I and rho one, something like this. And then this can guarantee stability. So now for the both question, uh, if the TR affect on the reaching time, so based on this different sliding surface, if we want to design the TR depend SMC, so for all these cases, so we can find the control signal based on a sliding surface. But the sliding surface again is very interesting that the sign function exists. But as I told you before, that if you want to reduce the chattering, if you want to reduce the chattering, so you can approximate it. You can approximate this with the ST divided by the norm of S plus epsilon, okay? And then you can get the less chattering. So another question is how to design a sliding surface for the larger scale system. That is very important. So if the system is a larger scale, a CPS or the minor system, how to design the sliding surface? So the high dimension, complicated transition, high requirements. So these are some difficulties we have for the larger scale. So this is a typical, basically the sliding surface. So we learn how to define it. So based on the parameter T psi and the T psi, it also has a dynamics. So if for this high dimension, because this brings you the high dimension, because for the largest scale, you have the large dimension X and AI, and this is a very large scale. So if you want to reduce, to get a smoother transition with the low requirement, the less parameter and computation, and the good system properties, so basically we can look at this kind of the sliding surface. So we can look at this sliding surface like this. So these are some new results, and that's it. So if you are interested, we can also discuss it. But in fact, we can do some modification. So in order to get some reduction of the dimension with the less computation. So these are the some research areas. Okay, so the large scale, the model, how to look at a sliding surface design. So we can do some modification like this, or there's some other challenges we have from the system. But in fact, I try to give you part of the difficulties we have from the system point of view and how to get connected to the control design. Okay, so this was the this part. If there is no question, I can talk about another topic. Any question? Or?
Sir, what is the effect of chattering?
Sorry?
What is the effect of chattering?
Okay, effect of chattering is destroying the system resilience in terms of the lifetime. You see, if the chattering exists in the system has always fluctuation. Fluctuation means the control signal has a lot of fluctuation, and over the lifetime of the device, it has it can destroy the lifetime or the performance, and that's it. Another problem with the chattering is the unmodeled dynamics. So I think it's a very good question. So maybe I can write it on this here. So just I can maybe just a moment. I can write it down on the surface. So okay. So this question you asked me is a very important question. So if I want to answer it like this, uh, so the chattering. So the chattering, it has a bad effect. So over the lifetime of the system, because the system can get some troubles after the long term of operation. The second problem is the unmodeled dynamics. So we call it the unmodeled dynamics. So, sorry, so this is the unmodeled. So unmodeled. I don't know. I want to write it here. Unmodeled. Okay, unmodeled. Okay, unmodeled dynamics. It means that, for example, when you say that x dot equal ax, for example, plus b. So this is your system. So based on some information from the matrix A. But maybe you have ignored some dynamics like the T psi, for example, is equal, for example, A1 x plus, for example, A2 T psi. So this is we call it the T psi is the unmodeled, okay? So it means that this dynamics so has not been considered in your formulation. So when your control signal is designed based on SMC, and if it has a chattering, so in fact, maybe some dynamic has not been modeled in your formulation, but they exist. So I can give you one example. So X could be the position signal, for example, X could be the position signal, and the T cell is maybe some dynamic from the electrical machine, okay? From the electrical machine. So now if you have neglected these dynamics in your control design, but in reality exists, unmodeled dynamics in the reality exists, exists. And therefore, so if the dynamics can be excited, if at some frequency, so these dynamics of the unmodeled dynamics can be excited, then the system become out of control. Okay, the chattering has an infinite, the chattering has the infinite frequency, and they can excite the whole frequency, the whole frequency, and therefore, at any time, you should expect that some frequencies, but the high frequency for the noise, because of this unmodeled dynamics can be excited. And then if these T cells excited, you can only guarantee a stability for X, but you don't have a guarantee for T cell. And therefore, this is very important. So this was the reason that in the chattering for SMC, so I told you before that there is a one important topic about the zero dynamics. So zero dynamics is a part of this unmodeled dynamics. And if you want to control the chattering, you need to control the zero dynamics. So in the previous presentation, told you something about the zero dynamics. The zero dynamics, if you could control the zero dynamic, it means you can control the chattering. Why? Because the unmodeled dynamics cannot destroy the system performance. Okay, so this topic is a very important topic. So therefore, the topic of the unmodeled dynamics in the control and unmodeled dynamic in the measurement. So usually, because when I'm teaching to my students this topic, so we have the unmodeled case, so the unmodeled dynamics. So in the two parts, one in the control and also one thing in the measurement. So in the measurement is a sensor model, okay? So perhaps some dynamics cannot be appeared as some frequencies cannot be appeared in the frequency of your sensor data. And then if you look at the matrix y, so y as a cx, so maybe some parameter like the c1 multiplied the t size, so this has been neglected. So only you can see cx. But this information maybe appear in your basically the measurement. And that's it. We have the unmodeled dynamics in control, unmodeled dynamics also in measurement. And therefore, it's very important how to look at this problem. And if you want to control, so this part, you need to pay attention to the zero dynamics, and this is a topic of the basically the control in more detail. But I didn't go to the detail of this part because we have other topics, no time to go to very deep in each particular concept. Okay, do you have any other questions? So I see one hand raised. Any question or?
Hey, so sorry to interrupt, sir. Sir, I have a question. Please
Yes.
explain Zeno phenomena.
Okay, so I will talk about the Zeno phenomena, I think tomorrow, because tomorrow we have another lecture about event triggering. Okay, so if you wait until tomorrow, then tomorrow I can discuss more detail about the Zeno phenomena. But very briefly, the Zeno phenomena should be avoided because at the Zeno phenomena there is no information to the controller. The control cannot be updated, and therefore the stability so is questionable. But usually when we talk about this kind of event triggering mechanism, so we should guarantee that Zeno the phenomena should be avoided, and therefore always we need to prove that this case cannot be happening.
Okay, sir.
Okay, okay. Any other question? Okay, so now based on a schedule, we have also another topic about the fault tolerant control. So you know that for your information that one of the very active topic in my research group in Italy is about the fault. And that's it if you are interested to do some industrial project or some other theoretical project. So you're welcome to contact me. But I try to give you some introduction to the topic. So I will first also I will show you some applications. So if you are interested, more or less, some of my research has been done about some fault detection and fault control for the wind turbine, and also some other aspects of some offshore technologies. Because in your country, in India, so there is a high potential to do a lot of research on the offshore. In this case, so I have done a lot, several years research on the offshore mechatronics. So now you can think that the offshore CTS about the cyber physical system for the offshore. There is a lot of complexities, and also you can look at some issues related to the wind turbine. So anytime you have a question about this, you are welcome to contact me. And because these are the very hot areas for the energy, so specifically for India, so perhaps there is a lot of investment or a lot many projects in your country related to this technology. So about the fault, so basically there is a one concept in the automation decision supporting tools. So it seems that we need to look at the output and the cost. So the output should be reliable. It means that we need to look at how to optimize the reliability, because output should always exist, and this is the reliability of the system operation. At the same time, you need to reduce the cost, reduce the operation and the maintenance cost. O means operation, O means the operation, and M means the maintenance, okay? So this topic is very important if you go to any business, so they try to reduce O&M. But if you want to do this, so you need to have a knowledge. So because if you want to see that how to get the plant knowledge or the system knowledge. So this is the business metrics. So the output should increase. It means the quality should increase, throughput should increase, and also availability should increase. At the same time, the cost should decrease. Operation maintenance costs, safety, health, and environment, this should be increased because all the safety, they also increase they can increase the cost. So it means that there is a trade-off between the output and the cost. But what is the question for the business? For the business means that they should find a trade-off between the cost and also the output. So this looks like a game. So that's it. We have a game of the plant reliability. So it says that I'll give you one example. Assume that you go to the one factory, so they should make a plant outage at March 1st of March. So they have make some planning for outage around November, for example. So after 6 months or 7 months. But there is a question that if there is some identification of the fault, there is some ID fault, it occur at this time. So there is a question. So can we make it to the next outage? So if because the company has decided to do some outage in this time, but suddenly you get some fault features at this time, maybe around, for example, May. Okay, so in the May you got this fault information, but now there is a question to the company: should we continue to the next outage, or should we stop and then try to solve it? So this is a challenge, because the challenge is the cost. Because in the company, in the business, the big challenge is the cost. If they want to stop it, there's a lot of the cost for the company, because there could be different type of the fault, and different fault has a different problem. So now the company should make a decision. So therefore, in the topic of the fault diagnosis and the fault control, we have a big issue about the decision making. So decision making, so this is a very important topic, because the decision making means, again, the cost. Okay, so now for you, if you want to how to solve this problem, we need some additional tools. Additional tools is automation with decision supporting tools. Okay, so how to use this information to solve this problem? So we need to come to some category of the health management system. So the health management system, so it was introduced for aerospace. If you go to some business or some companies related to the aerospace, so the health management system first was applied to aerospace. So health management system has 5 sections. The first section is about the incipient failure detection. It means how to detect the failures even before they substantially affect the performance. So you can detect the failure at the earliest possible time. The second part is you need to prevent of the fault progression. It means that the fault conditions, so before the second fault has been developed, you need to prevent it. And the third topic is about the prediction of progression from the fault to the failure. So this is very important. So you need to remember that the fault failure, if you don't control the fault and if you don't detect the fault, if the fault becomes the failure, is the cost, okay? Because the failure is the cost. A fault, it could be the lifetime. For example, the lifetime, maybe if the fault exists in the system, maybe the life is destroyed. It looks like a chattering. For example, the chattering, it could be similar to the fault, because there is one problem. The problem exists. But if you don't control the chattering, it's okay. But of course, the life of the system will be reduced. And again, it's the cost. But in the company, in the industrial application, important part is this, is the failure, because the failure is the cost, and then you need to repair, okay? And the repair is the cost. Okay, so now you need to do the accurate prognosis for the remain useful life, okay? And this topic is the RUL. If you go to any company for operational company, the RUL should be improved. You need to enhance it. So now there is a topic about the enhancement of RUL. And this is a very, very important topic. If you are interested, maybe if you want to do some project on the fall, if you want to apply for any research grants, enhancement of RUL is one of the key points. So another topic in the health management is the efficient maintenance planning. So maintenance planning is the cost. So you need to economize on the maintenance effort, ensure the best availability. And finally is the control. You see, fault to control laws. It means you need to develop the FTC. FTC, it means that is a fault, a tolerant control, okay? Okay, so you need to modify the control based on the current health condition to extend the life. Extend the life means enhancement of RUL. Okay, so in total, as a conclusion, the overall system helps for increasing R&M. It means the reliability should increase and maintainability should increase. At the same time, you need to minimize the operation and the maintenance cost. So in total, in any business, the R&M and O&M. So this is there is some sort of the conflict, because it's very difficult to enhance R&M and to reduce O&M. How to make it? You need to follow these 5 steps from number 1 to number 5. But of course, we are in control areas. Control areas is the number 5. It's not the number 1. People control, you need to go to number 1, number 2, number 3, number 4. And finally, you need to come to control. So that's it. If you want to do the research about the fault, so we need to follow some systematic approach from the failure detection, prevention, prediction, enhancement, and control. And that's it. If in my research group in Italy, so most of my PhD students also they work on them from number 1 to number 5, but mainly in this area. So that's it. In my research group, we are using the AI. So we are using the ML, artificial intelligence, machine learning for this case. But there is no time. Maybe if you are interested, you can contact me, because we are developing many algorithms for enhancement of this particular case. And for your information, that the next year in 2026, I will organize the 2026 is the World Congress on the condition monitoring. So if you search on the Google in Milan, I can also send you the information of the Congress. Is the World Congress is the World Congress on the condition monitoring. So if you are interested to this particular topic, so welcome to Italy. So the conference would be from end of August 2026 in Milan. Okay. So let's back to the fundamental definition. The first thing we need to know the fault. So the fault has a definition is an unpermitted deviation of at least one characteristic, property, or the parameter of the system from the normal condition. So now you see that the function FP, it should have some abrupt change. Like this is a permanent fault. Then maybe you have some transition fault for the short duration. Or maybe the fault is such an incipient fault. The fault is increasing with the one slope, for example, like this is increasing. Or maybe you have some intermittent fault with a different, basically the transient duration, and the fault can be occurred at a different time. For example, T1, T2, and also T3. So these are the We call it the intermittent fault or even the multiple fault. So these are the basically different faults you can see. So the failure is very dangerous. So that's it. Always, if you do the research on the fault, you should avoid any failure because the failure is a permanent interruption. It means the cost increase of the system ability to perform a required function under a specified operating condition. So what should we do? Because we are dealing with the fault. Fault means that you need to look at the data because you should look at your data. And the data, you need to get some symptom. It means that the symptom is one of the tools or the information. We call it the information. It means that if you look at the change of an observable quantity from the normal behavior. So if you see such information from your data, so there is some change. You see, there is a sort of the change from the normal behavior. So that's it. The normal behavior is expert knowledge. Okay. Because one question for you that how should I know that this is basically a normal behavior? This expert knowledge, and that's it. If you want to do the fault control, you should have a knowledge, and that's it. It's an expert knowledge based system, and that's it. We call it the expert knowledge. But the problem is that in many cases we don't have this knowledge because expert knowledge is expensive. If you want to enhance the safety of the system, so you should have some expert with a good knowledge. And this is difficult. In many business, maybe it's not possible to find such a person. And that's it. You need to look at your additional tools like AI, or you can generate some knowledge. And that's it. Nowadays in the AI and also in the machine learning, and also comes with deep learning and also some other tools like the generative algorithm done, for example. It means that you should generate some knowledge, but the problem is that in all of these issues, we have some issues about the reliability. So reliability, and that's it. So nowadays there is another topic. It's added X. XAI, it means that we need to do some explanation AI. So these are the some topics, explanation AI. So these are the some topics in my group in Italy. Also, we work on XAI. So why we should look at XAI? Because XAI, we need to look at the reliable information. Reliable information is similar to expert knowledge because we should know what is the normal behavior, and then we should get a better decision after observing the information. And that's it. The symptom is very important, but the symptom in the AI means the feature. Okay. So if you come to these topics, then you need to look at the features, and the features gives you different basic symptom. And that's if you are using the deep learning, or if you are using the machine learning. So you can look at how the feature can be extracted. And this feature extraction, the machine learning, the deep learning, or even if you are using the GAN as a generative AI, so you can generate different features. And it means that you are looking at a different symptom, but the classical intelligent approach. So you need to decide, or you can do both. And that's it. The research in the topic of the fault nowadays it goes through the intelligent approach, and that's it. And that's it. One of the topic I'm working on this area is intelligent fault fault diagnosis. So if you are interested to this kind of the topic, you can contact me. Okay, and then you are coming to the fault diagnosis. You need to determine the kind, size, location, and occurrence time of the fault. So you need to give some warning about the early detection. So this is the important about the determination of these are the type of the fault, location, and also the occurrence time. These are the information you need to get as in the context of the fault diagnosis. Okay, so now you see that we have a several keyword about the detection, isolation, identification, and also accommodation of the fault. So when you are using the fault tolerant control, if you are doing the FTC, so FTC, the fault tolerant control, you are doing the accommodation of the fault because you are trying to handle the fault. But if you want to do the FTC, the fault tolerant control, so you need to do you need to identify the fault, you need to isolate the fault, you need to detect the fault. It means there are several steps, 1, 2, 3, and also number 4. So if we do the some diagnosis, it means that the detection, isolation, identification is a diagnosis. So this is from the definition. Detection means indicate the occurrence of the fault. Isolation fault means determine the type or the location of the fault. Identification means determine the magnitude of the fault. So if you are doing on the accommodation of the fault, if the fault is a self-corrected, usually through the controller, you see? And this is a topic of FTC. So now if you want to know that why FTC is important and why we should do before FTC, so we should know that we have a two topic diagnosis. It means the detection, isolation, identification. And then you need to come to FTC about the accommodation of the fault. But as I told you that the FTC is not the first part. The first part you need to go to this step. Because if you don't have the knowledge about the fault, it's difficult to design the FTC, the fault control. Okay, so these are again the diagnosing step, detection, isolation, and identification. So it means that if you look at your XT, this is your profile, and then at this time, the fault has been occurred, okay? And this is your XT, this is your XT, and this is your X, okay? At this time, at the time TO, the fault has been occurred and the system has such a response. You see, it's out of the control. And then at the time TD, the fault has been detected. So now it takes this time. So the TD minus a TO is the time duration. So the system can detect it. So when the fault is detected, the fault, it takes some time to be isolated, and that's it. There is another time, T isolation, is a fault isolation. And then after this, the system can accommodate the fault. It means that after this, the system becomes in the good operation. So in total, in a time, so the system is usually it doesn't have a good performance, and that's it. So you should isolate it as soon as possible in order to get the system to the normal operation. So this topic, we call it the monitoring, or the topic of the condition monitoring, and this is a basic condition monitoring. So that's it. And next year, we are organizing the World Congress on the Condition Monitoring 2026 in Italy. So we are always discussing about all of these challenges. So when you look at the system point of view, so here we assume that we have a plant with a control signal, with a sensor. Here you have a sensor. And then you have some information like a disturbance. So here you have a noise. And also you have basically some fault in the system. So like the FT as a basic fault, okay? So if based on this control signal and your sensor data, so you want to do how we can look at basically the fault the detection case. So if you want to do the fault detection, you need to do some processing of your data. So this processing is based on the residual processing. But that means you need to have some additional information. So this information should be created, residual information. So what does it mean, the residual? Residual means information. One information is, for example, you call it the error signal, this error signal. The error signal is a y minus something. So this could be y hat, estimation of the y. For example, you can put y minus y hat, okay? So how to get y hat? You need to add the copy of the system. This is the model is a copy of the plant. So you need to put one model, but the model is again is the knowledge. Okay, this is a knowledge, and that's it. So this topic I'm talking the whole topic we call it a model based. Okay, this is a model based. The model base is difficult because model base, you need to have a model and the model is a knowledge. Okay, so, but anyway, if you're doing a model-based fault diagnosis, so you can get the error signal as a residual signal, and then this signal should be produced. This signal should be produced, okay? How to produce it? So you can do like this. The RT is coming after the processing. So now what is the processing? So this processing sometimes, because RT is you want to make a decision, because after the RT, so you need to make a decision. So what is a decision? Decision means if there is a fault or not. So if you want to make a decision, you need to look at your signal RT, and the RT has been generated after this. So now you need to see how to make it the decision making. So you need to look at your error signal and then to do some processing after. I will tell you later on. So another approach is the fault diagnosis as a two-step procedure. So in the two-step procedure, so you have a plant. So maybe you have a fault, for example, F1, or maybe you have a fault in the sensor FS, or maybe you have a fault in actuator about F8, okay? So for all of these fault in the plant sensor actuators, so now you need to get your information. Information, again, is the sensor information and also the control signal information. So you can take it to additional block as a model-based fault detection. It means you need to get the plant model, and then you need to get the residual generation, and here you will get RT, okay? So if you want to get the decision, because this is the decision, so if you want to get the decision, you need to do some residual evaluation. So this residual evaluation, so it depends to the type of the signal. If the signal is stochastic, or deterministic, so there are two different evaluations. So evaluation for a stochastic signal or evaluation for a deterministic signal. So, okay, so what should we do if we want to do the research in the context of the model-based fault diagnosis? First, we need to make a copy of the plant. The second is how to generate the residual signal. So this is a very, very important. So important is here. So for example, sometimes you need to look at the current signals, okay? You need to look at the current signal, or you need to look at some vibration signal, okay? So it means that if you want to do the research in this topic, so you should remember that which signal should be taken to be as a residual generator. So because the problem is that in some signal, the symptom of the fault cannot be appeared. So if you have any complex mechanical system or CPS, If the fault occurs at one point, this information maybe cannot be appeared in other data or the other sensor data. So now important for you is that which signal should be taken or should be monitored for the fault diagnosis. But please remember that you cannot monitor all the signals, because if you want to monitor all the signals, it's very expensive, because you need to deal with a lot of data, like the big data. There is a lot of sensor data, and you are not able to monitor all the data. And this is one challenge. Okay, so if you finish the part of the residual generation, and if you find RT, then you can do the evaluation, and then you can get information about the fault. Okay, so the fault diagnosis and also isolation with control system. So this is the topic, more or less the control becomes the main, has a main role. So here we have again the fault in this process. So for example, again, you have a fault in the process, or the fault in the sensor fault, or even you have the fault in actuators. So as I told you before, that you can get information of the sensor, and also you can get information of the controller. So to one, the part as a fault diagnosis, okay? In the fault diagnosis, you can get this information of the U, and also the information of the Y. And then the result of the fault diagnosis, so it could be also given some input to the control design, redesign. So control redesign or the control change is the FTC. So that's it, the control redesign. So is a part of the fault tolerant control, because it can directly affect on the control design. And then you can design for example, control signal. So the benefits of this approach is to get the early detection, gives the higher availability. You can reduce the maintenance cost and also avoid the wrong dosing. When sensor has a drift with it, you have some drift in the sensor. But this particular part, you can also do some analytical redundancy. So this analytical redundancy means that so you can get two information. One information is the control signal U, and also again the control signal Y. Okay, so here you give the U and Y to the fault diagnosis, but now you can also give the U and Y to another part as the analytical redundancy. So you want to duplicate. You want to duplicate your data processing. And then based on this model you have in the analytical redundancy, you can give additional information to the fault diagnosis. So this information just to help us to get the better decision and the better residual signal, and then for the control reconfiguration or the control redesign. So in this case, for instance, this was also I showed you before that assume that these are some oscillation index from your sensor data. So if you put some threshold, and this threshold, it says that on the top of this, the fault can be occurred, okay? So now you can see that if this sample data is above of this threshold, it means that at this position, the fault has been occurred. Okay, the fault has been occurred, and then if you do some processing on your data, and then you can see that, for instance, after this reconfiguration of the controller fault diagnosis, so it can see that at this time, at this sampling time, so the fault has been basically controlled, or has been the problem has been solved. So now you can see that this time frame. So there's a time frame that the fault exists in the machine, and all of this point you got it is above of this sampling point. So, and now the big question is that how fast, so how fast you are able to detect basically the fault in the machine. And this is that's it. We can use this kind of analytical redundancy. So just to help us to get the fault be detected as soon as possible. So for the fault isolation scheme, so there are different schemes. One is a dedicated scheme, one is the generalized scheme. So it means that in the dedicated scheme, we have a set of the residual signal can be generated. So in this case, so each residual is sensitive to one of the fault only because you remember that the R signal R as a residual signal is coming after the some part as a residual evaluation. For example, you can give the error signal to one block, and then you can get the R, okay? And this is a residual generation. So now the point is that this signal RT you want to generate it. If you are doing the dedicated scheme, it means that it should be the sensitive to each particular fault. For example, for the fault number one, so then you can see that basically this should be for example the R for example one. So all the sampling time should be bigger than T1. So what is the T1? The T1 is the threshold. So this one, the T1 is basically it shows a threshold, and FK is the fault, but the fault for the index number I. It means that in this system maybe you have a J, you have a G number of the fault. Okay, so for each particular index, for each particular fault, you should have one particular threshold signal, and then you can basically satisfy this condition, and then you can do some dedicated scheme to detect the fault. Or you can use the generalized scheme. So here you have again a set of the residual signal should be generated, where each residual is sensitive to all but to all fault. So in this case, but only one fault. So basically, it should be to get rid of the one particular fault. So again, so you see that this RJK, it means that your residual signal should be bigger than PJ. For all the particular, basically the faults you have in the machine, expect a number I. For the number I, so it means that the RIK should be less than TI. So again, in the context of the generalized scheme, you need to find the set of the residual signal should be generated in such a way that so each residual should be sensitive to all fault except the same one particular fault, for example, number I. And in this case, you can develop basically this scheme. Okay, so now you have this kind of fault isolation scheme, and then you are able to look at the detection part. So we have the topic of the detectability and also isolability. So the detectability means that the fault number I, FIK, it can be detectable if there exists a stable residual generator RK. So this signal should be affected by FIK. This is very important. So I told you before that if you want to detect the fault number I, you need to choose the right signal, the right residual signal, because RK should be enriched. So should be enriched. It means that this should contain information of the fault FIK. Otherwise, you are not able to detect the fault number I. So isolability means that the fault number I, FIK, is isolable if there exists a stable residual generator such that the FRK can be distinguishable from other faults based on RK. Okay, so this is about the isolability and also detectability. So up to now, I discussed about the model base. So for the model base, you see that starting from 1971, with the PhD thesis for the purpose of work about the fault detection for linear dynamical system. So 1975, the observer-based techniques, 79 about the parity relation methods, 1980 about the two-state diagnostic procedure, 1981 about the robustness in FTI, the fault diagnosis and isolation, and then in 1986 about the FTI for nonlinear system, and then 1988 there is some progress about the adaptive threshold-based techniques. 1989 about the subcomputing technique for FTI. 91 about the FTI in nonlinear system. And then you can see that the establishment of the IFAC on the safe process for the fault detection, safety, and supervision. So this conference, the safe process, so it was built after 1991. And then if you come from 91 up to now in 2025, so you can see that there are many research. So, but I want to tell you that the research approach, the model based, so it's also important, and also the some data driven approach. So that's it. So not there is a lot of focus on the data driven the part. But data driven becomes more and more important, and that's it. What we are doing, and we are using the AI, machine learning, deep learning, and so on. And if you are interested, I think that we can discuss more because this is the topic nowadays has a lot of interest. So another important thing about the residual generation, because the residual generation, and then you need to come to the residual, you need to come to residual evaluation. Okay, so these are the two topics. And then you can make a decision. You can make a decision. Okay. Okay, so if you want to go to the first step, residual generation, you can do different techniques like a fault detection via the quantum estimation, or you can do the observer-based approach, or you can use the parity vector approach. So here, these are the some techniques. So you can use it basically for the residual generation. Okay, I will tell you very briefly about the residual generation. So as I told you before that the two information, input signal and the measure signal, you need to take it to this part. So this part you need to make a model. The model is basically is a copy. You need to make a copy of the system, and then you need to make some estimation. You need to make estimation, and then you can get the delta P. So delta P is some information. So this information, but because you need to use it for the residual generation. Okay, so now for now I want to tell you how to make it. So for this particular case, so if you use your input signal and also the measure signal, so you can take it to this part, basically to make some sort of the estimation of the model of the system, and then this should be also dependent to some change of the counter estimation. So you can get the theta hat of the counter estimation. So based on the error signal ET. So here in this residual generation via the counter estimation, first of all, the error signal is a y minus a y hat theta t. So this is the y hat here. Okay, so it depends on the theta and also depends on the time. So the theta, so basically, so for this model of the y hat, so the y hat, it depends to this p hat over a hat, multiply the input signal you set. So this is your estimated model. Here you have this estimated model. But this yt, so here you have as a measured data. So it can be also parameterized in terms of the theta, because the theta is a one parameter. So you can basically represent the yt based on the side transport. The theta is just uh, how to parameterize. So the measure signal in terms of the vector of the theta. So if you look at this, so the delta yt is the side transport delta theta, because if you look at the deviation of your measure signal, because it's a deviation of the measure signal, it can follow this mathematical formulation. It's a side transport of delta theta, delta side transport theta plus this. So this deviation, it says that deviation in the measure signal, it has a deviation in the theta, deviation in the psi, and also the deviation in the both information, the theta and also the psi transport. But we need to remember that the parameter the theta, this is also the function of the physical process coefficient. It means that the theta here is equal to fp. And this is a function of the some physical parameter, the p there. So this parameter p is basically the physical parameter for the system. And then based on the delta y, you can also get delta p. The delta p is the residual signal, as I showed you before. Based on this strategy, we need to get delta p. And it says that if we choose the residual signal delta p, so then the fault has been contributed to the fault diagnosis problem. Then this signal could be a good signal for you because it contains information of the fault. Okay, so this slide, it shows you that how to use a model-based approach for the residual generation of the signal delta p based on the parameter estimation. So this is some typical or a standard approach. So this is again the same delta p. So I showed you before. Okay, so this approach has some advantage and also some drawbacks. So one advantage is that the model has to be linear with respect to the parameter. It means that this is one limitation. So the detection of the fault in sensor and actuator is possible, but rather complicated. So now you need to have a suitable transformation of the parameter deviations into this fault has to be determined. The detection or isolation of a parametric fault are very straightforward. So this approach is also the detection or isolation is very straightforward, and also a value of the online parameter estimation method can be applied. So this approach, you can use different estimation. You can use the Leuenberger observer. You can use the Kalman, or you can use extended Kalman. It means that you can use different estimation techniques for basically for this part. Okay, so another approach is about the parity-based approach. The parity-based approach is one starting point to the data-driven approach, because you can deal with the data, not with the model directly. So in the parity vector-based approach, so you can look at some analytical redundancy can be performed by collecting the sensor output in a data window. So here you need to get your measured data. So your measured data, it means that for one, the time window, based on the parameter S as the size of the time window, so you can collect some data. So A starting point is what is the S, okay? So how to choose S. How to determine the size of the time window. So you can find this publication. So this publication can tell you that how to choose the effective size of the time window. But this is about the data, okay? So now you've got your data, and then you can form the dynamical model because the model can be fit as a linear form like this. And this model can give you some redundancy relation. So this is based on your data you have observed. This is your collection data. So this is the sample data from this time window. So that's it. You have this measure data. Then you can find the relation between the measure data and also your input data. The input data is also the different the time data you have collected for the control signal. So this data, if you put in the vector form, it's a one vector y, okay? And the data for the control signal is you can put it in the one vector, it's a UK. So now you can see that the UK and the YK, there is a matrix H. They can also relate each other, these two vectors. But it's very interesting to see that this formulation H1 and Y is equal HUK. So it can be also written like this mathematical model. Why from here? Because if you look at here, the Y, it has a relation to XK, UK, and also FK. So that's it. The UK as a control signal, it also has information of the vector X, and that's it. So these two parts, so you can represent it like this formulation, so like the WXK minus S, and this particular form for the fall can be written like this. So what is the conclusion? The conclusion, it says that information of the YK, your data, it has the information of a state and also information of the fault. And these are the fault information and these are the system information, right? These are the system information. So now based on this data, if you want to use this parity-based approach, so you need to make a decision based on this collected data, how to generate how the residual signal, it means how to generate the residual signal, and then the design procedure could be like this. So a residual signal is RK, okay? So you could say that the RK is equal matrix V multiplied YK minus HUK. So if you write this formulation, because this is up to you, because this is a procedure, RK is a V multiplied like this, but we don't know what is the V, okay? We don't know what is the vector of the V. And this formulation becomes VW based on this mathematical model. So based on this mathematical model, so this can be written that V multiplies the omega xk minus S and plus a V and Fk. Okay, so, but if you want to get this formulation, it's very interesting because the residual signal has some information of the system xk minus S and also information of the fault Fk. But if you want to get this condition, you need to set V multiplied by W if you choose the vector V, such a way that the V omega becomes zeros and the Vm is not zero is very useful because if the V omega becomes zeros, it means that your information of the state, information of the plant can be removed. and only remains information of the fault because the VM is not zero. Then if you do some analysis on the RK, then you can make a decision about the fault because RK contains information of the fault, not information of the system. And that's it. If you want to apply the parity-based approach, you need to remember that you need to find one matrix like a matrix V, but this matrix V, so when it's applied to the omega, this should become zero and this should become non-zero. Okay, so the main advantage is useful for designing a set of the residual that can be applied to sensor and actuator for the FDI, the fault, the diagnosis and isolation. So another approach is the observer-based residual generator. So this approach is like this. So here you have a plant. So this plant, you have the YK, and this information of the YK, so you can bring the YK and also the information of the UK to the plant. And then here you can put you can design the observer, so you can use the Leuenberger or the Kalman filter, and then you can get estimation of the y hat k is a cx hat k, and here you have a y is a cx, okay? And then you can see that the RK can be generated based on these treatments. So here I can show you some formulation. So assume that this is the information of a state of the system, and this is the measure signal. So here you can see that the fault exists. Fk is the fault, and the omega k is the noise. Without the noise, and then you have a fault. You have a noise. But for your information, if you want to do the research on the fault control or the fault detection, important is how to look at the noise. So you need to deal with the noise because the noise at any time can make a problem to make a wrong decision. And that's it. The noise should be controlled, and that's it. We need to make a more consideration how to deal with the effect of the noise. So in this problem, the noise is in the process noise, and also we have like a measurement noise. So if the system is a deterministic, for deterministic system, you can design the Leuenberger observer, okay? So the observer is like this, x at k plus 1 is a at k x k plus 2k u, and plus the observer gain kk plus 1 multiply yk minus y hat k. Okay, yk is this information, and the y hat k, so it's also the estimation of the from this formulation cx hat k. Okay, we can put it here. What about the RK? So this residual signal, you can get it from the RK. So you say that it's the YK minus Y hat K. So now the RK plus 1. So RK plus 1 is the YK plus 1 minus Y hat K plus 1. So if you follow this mathematical formulation, you can get this box. In this box, you can see that the RK plus 1 has two information. One information is information of the plants. These are the information of the plants. And this information is information of the fault, okay? So now it's very difficult because the information of the fault, information of the basically the system are mixed, but you need to do some good evaluation in order to detect the fault. But if you have a stochastic system, for a stochastic system, you can use the Kalman filtering. So you can write down the equation of the Kalman filter equation. And then you can also write down this index function, the residual signal. But here the problem is much worse because the RK for the Kalman filtering, one part is the system information, and this part is the fault, and this part is the noise. So now you can see that the noise, fault, and system information now is very difficult. If the system is stochastic, there is a noise. So you need to make a better evaluation about the fault the decision making. So in this case, this research is a very hot topic. So if you want to do the residual evaluation for deterministic approach, for Lübeck is very easy. You can use the fixed threshold, but for a stochastic approach, you can use different techniques like the weighted sum scale, residual testing, or the X2 testing, or the sequential probability. You see that there are a lot of techniques has been developed in the literature, but basically for the residual evaluation. Because after the evaluation, you can take a decision, and then you can make a call. Okay, so for the FTC architecture, so as I told you that here we have a control plant. You need to do the monitoring system for the fault diagnosis. And then you can do the some reconfiguration for the control part. And usually the FTC, it contains the FD, the fault diagnosis, and the control all together. You see this dash box. And then you can do the fault tolerant control, including the fault diagnosis and also the fault accommodation or the reconfiguration. So if you want to see that how we can do it for the FTC, so for the nonlinear system, you need to look at your measured data, XT, you need, and also the control signal. You need to take this information to the fault detection and approximation to the FD, and then you need to make some decision, making some decisioning. And based on the fault that the decision making has been done, the fault has been detected, and you can take it to the bank of the fault isolation estimator, the fault isolation decision scheme, and the fault can be isolated. And also this information of the fault can be taken to the control. So after detection of the fault, you can do some fault accommodation and also control the configuration, and then apply the control signal to you. What does it mean, reconfiguration? Reconfiguration means that, let's assume that you design the PID control, for example, KPX, okay? Assume that you use the P control. So when you are using the reconfiguration control, you need to change KP. You need to change it to another K. And this change of the coefficient of the control is a control reconfiguration. Okay, so, okay, I think very briefly for your information that, so for the fault detection, diagnostic, and the prognostics, so the umbrella is the condition monitoring, CM, right? So that's it. We are organizing the next year, the World Congress in Milan. So condition monitoring means the fault detection, fault diagnosis, and the fault prognosis. So if you are doing all this step, you can do the better maintenance. It means the cost basically can be reduced. But another information for you is about the uncertainty, about this uncertainty in the data set, and also the complexity. But if you have the uncertainty as a static or dynamic, and then you can see that for the complexity of the system from the low variable, the high variable, so intrustive or the non-intrustive, then you can see that the CDM is a condition-based maintenance. RCM is a reliability center maintenance, and the robust design. So now you can see that for the low complexity, with the less uncertainty, you can use the condition-based maintenance. But if you have a more uncertainty, if it's a stochastic, if it's a static or dynamic, So basically, you can look at the RCM as a reliable center maintenance, and also you can look at the robust design. But if the complexity of the system increases, for example, CPS with a high complexity, then you can see that you need to look at the e-maintenance for the low uncertainty. You can use the PHM, so it's a prognostic and health management for this level of uncertainty. But if you have some dynamic uncertainty, you need to make the system more resilient system. But for the non-intrusive complexity, so with the high value there, so you need to look at the preventive maintenance, self-maintenance, and a unit immune system. So now you see that this table shows that how to look at the difficulty in the data if you have some uncertain data set, and how difficult is the complexity of the system. So now, usually in engineering, the RCM is a very important topic, resilient for the more dynamic uncertainty. So then these are the advanced topics that we have in the topic of this topic. But of course, I can stop here, but I want to show you some application. Maybe later on, if we have time, I can show you some application to this topic. So if you agree, we can have a break. So any question, or do you have any question, or?
Sir, actually, I have a small query related to your previous discussions on dynamic event triggered. Somewhere you mentions that the parameters through which this event trigger strategy is to be ensured, either that has to be computed adaptively or by the neural network approaches.
Yes.
So, sir, if I go with the adaptively updations of that parameter for smooth transmission, or for ensuring the smooth transmissions of the data, then how can we obtain this dynamical equation for this rho t? So is this equation will come from the Lyapunov theorem, or how we can go for the calculation of this rho t dynamics?
Okay, yes, it's a good question. So the rotate, you can either add some learning, you can add the AI. So maybe you can use some, of course, there is some adaptation. So for example, you can say that, just for very briefly, you can say that the rho dot is, for example, minus the gamma rho, for example, plus something. So it means that either you can use some learning part, or you can use some adaptation. And for these parameters, these are some parameters you need to play, you need to use for the design. So that's it. Usually this topic is the learning base. So, but sometimes the learning could come from the adaptation, or sometimes the learning comes from the neural networks, okay? And in both cases possible, but importantly, so you need to represent some dynamics. Dynamic means the rho dot equals something, and this formulation, so it's a very explicit information. You have this explicit information, but some parameters basically should be tuned, and some parameters should be decided. But usually in the research, if you look at this publication, also I showed you before, then you can see that these parameters, more or less, they show some adaptation, and it says that the rho is not constant. Uh, I think then tomorrow I will show you some result, even for the self-triggering, and then you can see that how effective is the change of the rho in order to get the better result.
Sir, it will be very helpful if you can share some references related to this dynamic event triggered mechanisms.
Yes, I think you can look at this paper, you see.
Okay, okay, sir.
Yes, I think I put some reference. This published in 22 is about the dynamic event-driven mechanism. So, okay, any other question or? Okay, so I think based on the schedule, so we have a tutorial, right?
Yes, sir. Yes, sir.
Okay,
Sir,
maybe we can.
yeah,
Yes.
if it is possible, can you give a 5 or 10 minutes break?
Okay, maybe we can have it because we can start at this time. So what's the time in India? So it's, I think, okay, we can have a 10 minutes break, right? And then we can
Okay.
continue. Okay?
Okay, sir. Okay, sir. Thank
Okay,
you.
thank you.
Thank you, sir.